belonging. Some people die before they fulfill their desires. Such a waste of existence.
Oh, hey. Hey, what's up? It's the Double Tribble channel. How are you? My name is Ron. I live in rural New Hampshire. And I stream science and technology. And I'm live in an area with a bunch of wild animals and stuff like that. So I stream about that too sometimes. Today we're streaming about the twin paradox. A lot of you are probably familiar with the twin paradox. This is not a like an edited down video. If you're watching this on YouTube or on doubletribble.com or wherever, this isn't like an edited video. It's a live broadcast. This is going out live on Twitch, and so it's not going to be as polished or whatever. But it should be fun. We're gonna talk about the twin paradox, and I'm going to give some explanations that you've probably never heard before, and give you new insight on how I know about what the twin paradox is. Yeah, the thing might be interrupted sometimes. I've got a chat facility here. And people might come and chat, or anything can happen. Right? It's live, right? All right. So what we got? I put together a little animation. Right? When you do. Everybody who talks about the twin paradox, you got to have a cartoon animation. I'm pretty sure that's a rule, that you got to have a cartoon animation when you talk about the twin paradox. So that's what I'm gonna do. I'll play a little video here. Let me see if I can bring that up here. There we go. All right, and I'll put the title back on here. Did that work? Yep. All right, so this is the twin double to the twin paradox like you've never heard of it. This is just a little intro video about it. Okay, so I'll play this and I'll talk about it as it's playing. All right, so you got a twin that stays on Earth, right? Twin that gets in a rocket and goes and flies out several light years away over several years. Turns around instantly, comes back to Earth, and lands, as far as its retro rockets or whatever, and lands on Earth. And meanwhile, at Earth, there's another twin, right? The other twin has been on Earth, anxiously waiting for her twin to come back. And so she runs up to the rocket after it lands and opens the door, and what does she find? She finds a puddle of biomatter on the bottom of the rockets, on the floor of the rocket. All right, what happened? Why? Where'd the twin go? Why is there a puddle of biomatter on the bottom of the rocket? Well, the problem is that when the rocket, you're up in space there, the rocket turned around instantly, right, and fired it. It was going 99.9. Right, here's the thing. It takes off. It gets up to 99.9% of the speed of light. Travels several years, a few light years out, and turns around instantly and comes back. And so what happens when you turn around instantly? Well, the twin in the rocket did not have their inertial dampeners on, right?
Inertial dampers are offline.
Right. That was the problem. And so I did the calculation on this. If it took even like 3 or 4 minutes for the thing to turn around, it'd still be pulling a million G's of force. So of course that's gonna squish the twin inside the rocket. In fact, a million G's is gonna squish the rocket down. In fact, you can't. None of this would make any sense, right? It's a chemical rocket. It's not going to be able to turn around like that. So this is okay. So this just right off the bat, right? We got the twin paradox. Everybody who does the twin paradox, there's always something that's just not physically possible, especially not physically possible today, right? In the twin paradox. So, it's a thought experiment, right? We can think anything we want in a thought experiment. So we're going to think that this rocket here that's turning around has inertial dampers in it, so it doesn't get squished, right?
Inertial dampers are offline.
So that's what we're going to do. All right, we're going to pretend that there's inertial dampers in there, so it can turn around immediately, right? And that's kind of important. If you're going 99.9% of the speed of light, and you want to turn in, say you're going 99.9% of the speed of light, and you want to turn around and go back 99.9% of the speed of light in the direction you just came, you got to decelerate and then re-accelerate again. To do that in a way that you pull no more than 1 G, it would take over 7 years of time in the rocket's time to make that turnaround. On Earth, it's like 44 years or something like that because of the time dilation. So it's got to be quick, and so we'll use inertial dampeners to get this thing done. So that's what we're doing. All right, so let's try it again here. Let me see if I can get my video queued up again. Yeah. All right, so the rocket comes back, right? Rocket comes back to Earth, lands. He used his inertial dampeners. The twin runs up to the rocket, opens the door, and finds a baby. A baby. Wait, what? Why? A baby? Why is there a baby? Did the twin turn into a baby? Did it go backwards in time? What happened there? That's not. Is this the twin paradox? I don't know. It's a baby. The twin runs up to the rocket and there's a baby inside there. So something. I don't know. All right, I'll explain that in just a little bit. But that's kind of weird, right? It's got a baby in there. So. Let's break this down. All right, what's going on here, so we can figure out what the heck is the deal here. Let me load up a space-time diagram. Right, that's what everybody uses. And by the way, I'm going to be talking about stuff here. I'm going to be talking about the special relativity. I'm going to talk about space-time diagrams. And if you don't understand that stuff, then a lot of what I'm talking about might not make a lot of sense to you. I did do a stream a little over a year ago on September 1st on special relativity. What was it? It was titled "Why Astronauts Don't Age as Quickly" or something like that. Anyway, you can find it there on YouTube, and you can also find it on doubletribble.com. But I explained special relativity, and then a few days ago I did a stream specifically on space-time diagrams, which are whoops, that's not a space-time diagram. There we go. There's a space-time diagram. Yeah, this I did this one a few I don't know, was it less than a week ago? I did a stream. Did the whole stream on space-time diagrams because I knew I was going to do this stream on the twin paradox, and I wanted people to understand how space-time diagrams work. And it's more, if you think you understand them, it's more than what you think. you've got an x and y. Let me get rid of this one here, just to show you. You've got a t instead of y. It's t for time on this axis, and you've got x for space. Right, but it's a lot more than that. It's it's one dimension of space that we've got here. So it's not x, y, z. It's just x, and it's one dimension of time, which is all that we know about so far. But there's a lot more to this because with space-time diagrams, you can perform Lorentz transformations, and you can put multiple. You can display on the space-time diagram. You can display multiple frames of reference at the same time on the space-time diagram, which is very cool. So what we're going to do is we're going to this is the space-time diagram right here, and the thing is the first thing we got to do is we got to figure out which twin is the one that stayed still and which one is the one that moved. Okay, and this is the paradox. Okay, on the twin paradox, you've got a twin that stays home on Earth or in the spaceship, and in the other twin goes away and comes back. And on the typical way that they explain it is they say that the rocket goes away and comes back. Let's see here. So you got the rocket, and Earth, right? One twin on the rocket, one twin on the Earth. And either one could be still while the other one goes away. That's the way special relativity works, right? You got two inertial frames, and they're moving relative to each other. Either one can say that they are the one at rest, and the other one is moving, right? So what do you do about that? You got to figure out which one is the one that's moving, and which is the one that stayed still, right? Now I made this little animation up here. We just watched it, right? And it's very clear, right? The rocket is the one that went away and came back, right? The Earth didn't go away and come back. It was the rocket. And you can plainly see here. I'll play it and then you can see, right? All right, the rocket takes off. The Earth doesn't go away and come back. Watch. What the heck? Did you notice that the first time? The Earth went away and came back. Well, I'll be damned. All right. So the rocket is the one that's at rest, and the Earth went away and came back. Didn't notice that the first time, did you? All right. So the rocket ship is the one is the rest frame, and the Earth went away and came back. But wait a second. If the Earth goes away and comes back, right? It's gonna, you got the whole Earth going, and then it stops all of a sudden and comes back. We're gonna end up with the same problem we had with the rocket, right? We're gonna have the rocket. In fact, on Earth it's going to be worse, right? The Earth is going to stop and go, and all the oceans are going to splash up into space, and we're going to have a big problem.
The inertial dampers are offline.
Right. Okay. So, all right, we can do this. We can do the same thing. Oh, I got a chatter here. Hi, I'm not going to be able to respond to chat so quickly here. Disillusioned. All right, thank you. Yeah, I'm doing this mostly for the VOD, so I'm gonna be plowing right through the ads and everything. I'm just gonna present this thing, but I will take questions. If you want to ask questions, I'll get to them eventually. So let's say that the Earth has an inertial dampener on the Earth. Right? This is a thought experiment. We can think up anything we want. Nobody who does the twin paradox stays to you know, current technology and physical laws and all that, right? They always go off somewhere. So let's just say the Earth has an inertial dampener around the whole thing, and nobody nobody falls off, their oceans don't splash off or whatever. So the Earth goes away, right, and comes back, right? That's what happened. The Earth goes away like that. Rocket just sits here. It turns around just for fun, and the Earth comes back. All right. Let's play this again here. All right. All right. Right. Rocket is still. Earth goes away and comes back. All right. There we go. All right. So that's the story, and I'm sticking to it. Okay. Until we find out otherwise. And that is the paradox, right? You gotta pick one. You gotta pick which one is going to go away and come back, because that's relativity, right? So that's kind of a problem. I mean, it's not that big of a problem, right? We picked one, and we based it on something. We based it on what the picture showed there. So we're basing it on evidence, right? We've got video evidence that we're using to figure this out with. All right, so I already explained you got to know about special relativity. You got to know about space-time diagrams, because I'm going to get into that a little bit. Another thing you got to know about is acceleration. We've touched on that a little bit here. In classical acceleration is a change in a vector. It's not just a change in speed. A lot of people, when you say acceleration, they think speeding up, right? But it's more than that. It's a change in a vector, a change in speed, or a change in direction. And it can be a speed up or a slow down. Both of those are accelerations. So like if you're in a car, you're doing 50 kilometers per hour, right? That's an inertial frame, right? But if you don't change your speed and you turn the wheel, it's right. You're still going to feel an acceleration, even though you're going the same speed. So that's the classical way, right? It's either the direction or the speed, changing the vector. But when you get into relativistic stuff, it can be a little bit more abstract. It can be a little more general, and we can say that acceleration is a change over time of an inertial frame, right? Which is kind of the same thing, right? But we were talking in terms of special relativity and stuff. And one thing you find out is that you don't need mass. You know how everybody is getting squished and moved around and oceans splashed out into space and all that because they have mass, right? If something doesn't have mass, that doesn't happen to it. And a good example, perhaps the only example, is light. If you shine a light at a mirror and it bounces off, that light is technically changing its vector, right? It was heading in this direction, now it's heading in that direction, so that's an acceleration. The light has accelerated, even though light is always going the speed of light. It changed its direction, so technically that's an acceleration. So light can be accelerated too. When you get beyond classical stuff. So special relativity, it's motion at high speeds, really, because they use the term relativistic speeds. That means speeds at which the time dilation, length contraction, and other stuff becomes noticeable. There's no like hard cutoff of what relativistic speed is. And we're going to be talking mostly about time dilation here. That's what the twin paradox is mostly concerned with. But also length contraction happens. And if you do a really rigorous mathematical analysis of this twin paradox, you need to take that into account too. And we're probably not going to get into that much here. But yeah, either party there can be the one that's at rest while the other one goes away. All right, so we're going to assume that the rocket is at rest, and we're going to look at our space-time diagram here now. All right, so rocket is at rest. Let me show them here. Here's the rocket. Rocket is at rest at the origin. And the way space-time diagrams work is that the t-axis here is time. Again, this is the x-axis, which is space. And we're saying that the rocket is at rest. So this coordinate system here is for the rocket, right? Over time, the rocket is not going to go across the x-axis here. It's not going to go move through space. It's going to stay in one spot. So it's always here. And over time, this axis right here represents the what they call the world line of the rocket. The representation. The world line is not the line that the rocket travels in physical world, even though they named it that way. The world line is a representation of what the rocket's doing on this space-time diagram. So the rocket's world line, the way that we represent the rocket going through time, it's just going to stay right here in this axis. All right? But the Earth is going to go away and come back. So we got to show that. Before I show that, let me show you what this is what the path that light would follow. If you shot a light forward and backward along this x-axis, this is the path that it would take. And we set this space-time diagram up so that years would correspond to light years, and it's calibrated to light so that light is exactly 45 degrees here. But then we got to put the Earth on there, right? The Earth's movement. Let me get rid of the light cones. We don't think we need those anymore. The Earth is got to travel, right? And let me see if I can grab this here. This paint package is not the cleanest thing for doing this, but I'm going to try it anyway. Nope. Okay, I screwed up already. Sorry. All right, let me grab that Earth here and see if I can move the Earth. See if I can make the Earth move. All right, there's the Earth. So the Earth is going to start the origin too, and it's going to travel. Now I changed the speed here for this diagram. Instead of going at 99.9% of the speed of light, I made it 0.6 because it would be too hard to show on this diagram at that speed, because with the light cones here, let's see here. See these? If I did it at 99.9% of the speed of light, this T prime here, the path of the Earth, would be right on top of the light thing, and it just the whole thing gets kind of screwy. It's too hard to see what's going on. So we slowed it down to 0.6 the speed of light. You see what I'm saying? On our initial scenario, it was 99.9% of the speed of light, but in order to work on the space-time diagram, we slowed it down to 0.6%. It's the same concept, right? One's gonna age more than the other. It's not that big of a deal, but I just want to explain why we did that. So the Earth travels here. The first leg of this thing, right? The Earth travels out 6 light years away, and I have it going to the right, to the left. It doesn't make any difference, right? In the animation that I showed that video, it was going to the left, but it doesn't matter, right? We'll just make it go to the right here. It's just easier. Keep everything on the positive side of the graph here. So the first leg of the thing, it goes out to 6 light years away. Light year, right, is a measure of distance, not a measure of time. And in that time, from the perspective of the rocket, which is the coordinate system we're using here in the base coordinate system we're using, 10 years have passed. So 10 years have passed for the rocket, the twin on the rocket. The Earth has traveled out here 6 light years away, and that's represented by this line right here. But because of time dilation, because of special relativity, because the Earth is moving at 0.6 the speed of light, it's only going to take 8 years. Here's some of the formulas here. Right, velocity 0.6 c. You plug that into the equation for getting the gamma. Gamma comes out to 1.25. 10 divided by 1.25 is 8. So the Earth only experienced 8 years of time as it moved from here to there. All right, does that make sense? If you don't understand special relativity, of course it doesn't make any sense, right? It doesn't make any sense at all. So you got to understand special relativity, otherwise it doesn't make any sense. Trust me, this is what happens. Okay, and I might make mistakes. You know, I'm taking a stab at this. There have been so many people. There have been so many people who have done videos on this twin paradox, and almost just about every one of them makes mistakes because that's a complicated thing to present, and it's, you know. But everybody takes a stab at it, and it's just kind of fun just to do it, you know. And hopefully, I've come out with some ideas here and some concepts or whatever that maybe people didn't think of before, like the Earth having an inertial damper system. I don't know. All right, so Earth comes up. He gets 6 light years away, right? And it took 8 years of the Earth time and 10 years on the spaceship time. So spaceship Earth then immediately turns around and comes back to the origin, right? Immediately, without the ocean splashing all over the place. All right, let me put it down here below the rocket so we can see both of them. All right, and with the way that looks is like that. Right, so we get this is the world line of the Earth then. All right, as I said, it's not the line that the Earth took in actual space. This is a representation of what over time what was going on. So we got 8 little tick marks on this line here to get to here. Meanwhile, the twin in the rocket ticked off 10 years. Then the Earth turns around, comes back, ticks off another 8 years because it's going 0.6 the speed of light, right? And we've got a gamma factor of 1.25. The rocket ship, time on the rocket ship went 10 more years. And so the total time for the Earth was 16 years, and total time for the twin and the rocket was 10 years. So that's not right, is it? That didn't work out, did it? Because the twin on Earth is supposed to be older, and the twin on the rocket is supposed to be younger. So something got messed up there, didn't it? We got something got screwed up, and we don't know what it is. We got to figure that out. What the problem is there. And this is the paradox, right? There actually is something that I should mention here before we go any further. Yeah, let me show you this because this is kind of interesting. On this space-time diagram here. Oh shit! That wasn't supposed to. Let those dogs out. That wasn't supposed to. Who let the dogs out? As I said, anything can happen. Because Disillusioned asked, yes, because the Earth moved, and yeah, because did you see? You missed the video. We played a video at the beginning, and it was very clear from the video that the Earth was the one that moved away, not the rocket. Because in special relativity, again, in special relativity, either party can say that the other one is the one that moved, and they're the one that is at rest. You know what I mean? That's relativity. That's why they call it relativity. It's relative, to which perspective you've taken there. But on the video, it was the rocket that moved, or the Earth that moved, rather. So, anyway, that's my story, and we're sticking to it. But I wanted to show you one more thing here. Not only is the relative as to which one is moving here, Let me back this off here a little bit so you can see this. When the Earth moved from the origin out to here, 6 light years away, and it ticked off 8 years of time, from the Earth's perspective, the Earth says, hey, I'm the one that's at rest, and the rocket is the one that's moving, right? Because either one can say that they're the one that is at rest. The rocket says, no, I'm the one at rest, and I saw 10 years tick off, and you there on Earth, you guys saw 8 years tick off, and that's what it is. And the people on Earth, the twin on Earth, says, no, we're the ones at rest. We went 8 light years, or I'm sorry, we waited 8 years here, and got to this location here. And when we look back at you on the rocket ship, it looks like this. Whoops, no, it looks like this. These are the lines of simultaneity for the Earth in this reference frame, T prime. And lines of simultaneity are not the same for the person in a rocket, the twin on a rocket, and a twin on Earth. The twin on Earth, the Earth moved out here over 8 years, and from that twin's perspective, 8 years went by. But when it looks at Earth, at the rocket, it says, "Oh wait, you're on the rocket ship. The rocket is moving, so the rocket's clock is moving slower, and you haven't seen 8 years tick by. You've only seen 6.4 or 6.2 or whatever it works out to be years tick by. See, because this is the line of simultaneity here for that position for T prime for the Earth. So at this point, as the Earth is moving, and as the rocket is sitting still relative to the Earth, or as the Earth is sitting still, or the rocket is moving relative to the Earth, from the Earth's perspective, it looks like the rocket has only seen 6.4 years, I think it is, whatever it works out to be, because the lines of simultaneity are different for this reference frame. I don't know does that make sense? I explained it in great detail a few days ago when I did the presentation on space-time diagrams, and you'll be able to understand that. But the thing is that there is a paradox. There is kind of a paradox there. When you've got two bodies that are moving away from each other relative to each other, or moving just relative to each other, if this one says that it's at rest, then it can say that the other one, their clock is moving slower. At the same and in the same scenario, this one can say that they are the one that's still, and the other one is the one that is moving, and therefore this other one's clock is going slow. So each of them can say that the other's clock is running slow, which is kind of bizarre, but it works out because they're not in the same inertial frame, and each of them have different lines of simultaneity, so they can get away with that. I know it's hard to understand. It's hard to get your mind around it. It's one of these, how can that be? But that's what it is. So looking at it from the Earth's perspective here, let me show you this. Looking at it from the Earth's perspective, this is the Earth's world line and their reference frame. And their lines of simultaneity run this way. And so they think that the Earth's clock is running slow. But if we look at the lines of simultaneity for the rocket, and cut off those other ones. So the rocket is in this perspective. The rocket is just sitting there still, and 10 years go by for it. And it says, 10 years have gone by for me, but here's my line of simultaneity at 10 years. And it corresponds with where the Earth is. And Earth has only ticked off 8 years on its world line. And that's how it works. Either one can say that the other one's clock is running slower. So that's kind of weird, huh? So I don't know if we haven't come very far here in figuring this thing out, because we worked it all out, right? And and the twin on the Earth was younger, right? Because we saw in the picture there, we saw the Earth go away and come back. So the twin on the Earth turned out to be younger when we worked this out. So we haven't gotten, and that's not how it's supposed to work out, right? The twin on the rocket is supposed to be younger. So we got to figure this out. Disillusioned. You said, yeah, whoever is moving is going to be the younger twin. That's right. Whichever twin is the one that is moving is going to be younger. But the paradox is either twin can be moving in relativity, right? When the two objects are moving each other in separate inertial frames, either one can say that the other one is moving. That's the paradox. So we got to figure this out. We got to figure out how we can pin this down and get the answer that we're supposed to get, that everybody else got, and that was that the Earth twin is older than the rocket twin. Now we can look at some. I think what we'll do is I'll play some videos from the that other people have done. This would be kind of cool, actually. Let me see if I can do this here. All right, there's my video with the rocket. All right, let me see if I can find. I made a little montage of the some snippets from other YouTubers who have done the twin paradox, just to get a feel for what they're talking about in some of their things. And I'll play that right now here.
She has to accelerate, which means she's no longer in an inertial reference frame while she
was in the ship. And in order to do that, she needed to accelerate in order to turn around.
And it's in that brief half-turn that everything changes. Turning the ship means accelerating.
What actually changes the passage of time is acceleration, a change of velocity. Velocity.
The way to state the rule is to say that the man who has felt the accelerations, who has seen things fall against the walls and so on, is the one who would be the younger.
World line is non-inertial because he will experience a fictitious force when he changes direction.
Fire your rockets to start heading home, and during that acceleration, your notion of time would have very, very quickly rotated through the missing gap in my journey.
Then the observer B would start accelerating, and the A clock would speed up rapidly. And for Alice to get to the star, she has to change direction. And to change direction means she has to decelerate to zero and then accelerate again, or sort of go in a
factor in resolving the paradox is acceleration, while others say you could still get a paradox without acceleration.
Of course, we said Alice very quickly turns around and comes back, and
at a certain point, it will decide to decelerate and start accelerating again towards the Earth and return until it lands on the Earth.
Mainly, there is a version of this experiment in which there is no acceleration whatsoever. That's right, and when I saw it for the first time, the setup where there was no acceleration, I was floored. I was like, oh my God.
Feel the vibration of the engine. He can feel himself getting pushed into the floor as the rocket decelerates or accelerates. He can feel it turning around.
Paths are constant velocity. The curved paths are the accelerations. So yes, there are 3 sections where rocket clone is accelerating.
All right, so that was a whole montage of there are a lot of people out there have talked about it. And that's just not even half of them out there. There are a whole bunch of them out there talking about the twin paradox. And I've got all these ones that I've put here and more. I've put into the notes, the description for the video, and it'll also play them at the end as credits, and you can go and watch the ones that you want to watch and see how they cover it too, because you're not going to understand this the first time you hear it. I guarantee, unless you're Einstein, right? Because he's the guy who made it up in the first place, right? Unless you're Einstein, it's going to take you a couple exposures to this to understand it. So there seemed to be a theme there when they're talking about acceleration. Acceleration seems to be the thing to tell who is who there. Except you notice that Mahesh there, FloatHeadPhysics, he talked about a scenario in which there is no acceleration. And he's got a really cool video about that. You should check it out at FloatHeadPhysics on YouTube. And he talks about this scenario in which instead of having one twin that goes away and comes back, you got two twins or three twins, triplets, I guess, right? You got one that stays at the home base, and then one of them goes from the home base heading out, and at the same time there's a twin coming in from out, and then they cross, and they tell each other what time it is as they cross, and then it's supposedly there's no acceleration and under those conditions. The guy who made that up, I think, is the guy at Fermilabs. Let me just see space-time axis overlay. Let me see this here real quick. Oh, okay, that's something else. We don't need to show that. Okay, I'll play this video about from Fermilabs. This is Don Lincoln at Fermilabs. Fermilabs is a department in the Department of Energy, or a lab in the Department of Energy in the U.S. government, the federal government. So the cool thing about that is anything produced by the U.S. government is public domain. So I can play it without worrying about it. So let me get this queued up here. Okay, here we go.
It's called the twin paradox. I'll describe the problem and the solution in a moment. I should warn you, there's some math ahead, but, well, that's what you guys asked.
All right, I'll just play this and let it run here. I'll comment on it if I have
I've made two videos about how time is viewed differently by two different observers. One is...
All right. All right, seems like we've got an echo there. But all right, technical difficulties, sorry.
I'll describe the problem and the solution in a moment. I should warn you, there's some math ahead, but, well, that's what you guys asked for.
All right, we got it.
Now, I've made two videos about how time is viewed differently by two different observers. One is called Einstein's clock, and it is the experimental proof that special relativity isn't crazy. And the other one talks about how to use time dilation properly and shows that you really have to be careful about how they use Einstein's equations. I've also made a couple of videos that introduce the equations, both the Lorentz transforms and the meaning of the Lorentz gamma factor. If you want the strong background you need to really understand this video, I recommend that you view these videos maybe in that order. They're all on the Fermilab YouTube channel. Okay, so the twin paradox. What's that all about? Let's start by explicitly stating the two core reasons that this seems so paradoxical. First is that all observers can completely accurately claim that they're the single unmoving person in the universe and everyone is moving around them. And the second thing is that moving clocks tick more slowly than stationary ones. Let's imagine that you have a pair of twins called Ron and Don. Don stays here on Earth while Ron heads off to Alpha Centauri, call it 4 light years away, at a speed of...
By the way, this guy presenting this here, his name is Don Lincoln, and my name is Ron. So it's Don and Ron. And I'm sure that's a coincidence, but I just thought it was kind of funny that his name is Don, my name is Ron. All right, I'll continue this here.
99.9% the speed of light. So for Don, the amount of time the trip takes is basically 8 years. 4 years for Ron to get to Alpha Centauri and 4 years to get back. But Ron is traveling at high speed, so his clocks run slower. For every time t Don experiences, Ron experiences a duration of t over gamma. And gamma is just equal to 1 over the square root of 1 minus v squared over c squared. C is, of course, the speed of light, and I showed where this comes from in the Lorentz gamma video. If Ron is traveling at 99.9% the speed of light, then v over c is 0.999. Substituting that in, you get a gamma of about 22.4. And finally, what you find is that while Don experiences 8 years for the round trip, Ron experiences just a bit over 4 months. So that's the usual thing with relativity, and some people hope to use this as a way to actually conduct interstellar travel. The astronaut ages more slowly and lives to get to their destination. Okay, so far so good. But now we have the paradox part. The paradox part comes from what I said early on in the video, which is that both observers can claim that they are stationary. So why couldn't Ron say that he is stationary and Don moves away from him and back? If that's the case, then Ron is the stationary guy and Don is the moving guy. Then Ron should experience a long time and Don should experience a short time. So that's the paradox. If each twin can say that they aren't moving, then they both can say that the other twin is experiencing shorter time. And that doesn't make any sense. They can't both be experiencing short time. Now, if you rummage around on the internet, you'll find several responses. One is that this proves that relativity is bogus and therefore you shouldn't believe it. But that's completely wrong and you absolutely shouldn't believe that answer, but that answer is out there. A more reasonable explanation is that there is something that breaks the symmetry between the two, something that makes Ron and Don's experience different. This approach uses the fact that Ron had to decelerate at Alpha Centauri and accelerate to come back. Further, in order to stop back at Earth, he needed to decelerate yet again. Don experienced no such acceleration, and, according to this line of thinking, it is the acceleration that makes the difference. All of the time dilation, which is to say the shortening of the time experienced by the traveler, occurs during the acceleration periods. However, this explanation is totally wrong. Now, if you thought this was the explanation, don't feel bad. Many physicists who don't work with relativity a lot believe the same thing, but I can prove to you why this isn't true. So let's do a thought experiment in the spirit of Einstein. I want to set up a situation in which no acceleration occurs and show that time dilation does occur. And I'm going to do this with some equations. I won't go into the gory details, but I'll show the key points. Before I do, I want to remind you of Einstein's equations, what are called the Lorentz transforms. They simply convert the amount of space and time one person observes to the amount of space and time another person experiences. If we just label two people as 1 and 2, and person 2 is moving with respect to person 1, then the Lorentz equations are just what we see here. I'll pause for a moment so that you can look at them. In my non-accelerating scenario, there are 3 observers with the unimaginative names A, B, and C. There are also 3 locations, which we call 1, 2, and 3. Location 1 is on the left, location 2 is a distance L to the right of 1, and location 3 is a distance 2L to the right of 1. When we start out, we put ourselves...
Okay, you notice that this situation that he's getting to now is not the twin paradox anymore. We've got 3 different things, people, and they're way away from the twin paradox. But the reason why he's doing this is he's trying to get away from this idea of acceleration being the thing that determines which twin is which. Okay, that's all this is about. But it's really not the twin paradox anymore at this point.
In the point of view of observer A. Observer A just sits unmoving at location 1. Observer B is at location 1, moving to the right at velocity v. Observer C is way over at location 3, moving to the left at velocity minus v. So what's going to happen? Observer B will head to the right, and observer C will head to the left. They will cross paths at location 2. Observer B will keep heading off to the right, and observer C will pass by observer A. All pretty straightforward, right? So here's what we're going to do. When we start the experiment, all 3 observers are going to start a stopwatch. When observer B and C cross paths...
Okay, something that he kind of glossed over here is he said, okay, if all of them are going to start their stopwatches at the same time, but they're all on different inertial frames on different locations, and you can't, right? How does that happen? Because there's no agreement as to simultaneity. That's one of the consequences of special relativity. There's no agreed upon simultaneity. So anyway, there's a few things like that. Also, he doesn't get into length contraction as that much in here, but that's okay. It's the overall deal here that we're looking at.
The center, observer B holds up a big digital clock that observer C can read. That clock records how long it took for observer B to go from location 1 to location 2. Observer C also writes down the time they see on their own stopwatch as they cross location 2. Observer C then travels back to position 1. As they pass location 1, they hold up a big digital billboard that shows the reading on their clock as they pass location 1, the reading on their clock as they pass location 2, and the amount of time it took observer B to get to location 2. You can then work out the amount of time it took observer C to get from location 2 to 1 and add it to the amount of time that observer B took to get from 1 to 2. And then you can figure out how long it took to travel from location to 1 to 2 and back to 1 again without any acceleration. So let's define 3 events, which we'll number with Roman numerals. Event 1 is when they start. Event 2 is when observers B and C pass at the center. And event 3 is when observer C passes location 1. To work those out, we need to figure out the location and duration of each event according to each observer. We can start with observer A. There are 3 places and times that are important. They are when the experiment starts, when the 2 ships pass one another, and when observer C zooms by. Remember that location 2 is a distance L away from observer A, and that, at least as far as observer A is concerned, observer B is moving to the right at velocity v. Thus, observer A would say it took a time equal to the distance divided by the velocity, or L over v, for observer B to get to the meeting point. Okay, I'm going to do some math here. If math isn't your thing, just let it roll over you, and I'll get to the punchline at the end of it. We can write those 3 important locations according to observer A as we see here. The space and time coordinates for A are 0, 0 for event 1, L over V for event 2, and finally 0, 2L over V for event 3. If you need to take a moment to work this out, go ahead and pause the video until you're comfortable with what I've said. Okay, now we just use the Lorentz transforms to figure out the position and time observers B and C see for those 3 points. It's important to remember to get the sign right on the velocity. As far as observer B is concerned, observer A is moving with a negative velocity, but observer C sees observer A moving with a positive velocity. So we can do that, and we find that observer B sees things differently. She sees those locations like we see here. And observer C sees things in yet a different way, which we can see here. Now, these aren't obvious. If you want to do the calculations yourself, just put in the x comma t from observer A into the Lorentz equations with the appropriate velocity, and it's actually pretty easy. Okay, so that's the hard part. Now we just have to figure out the total duration. We do that by subtracting what observer B's clock was at event 2 and event 1. We then need to do the same thing for observer C, except for event 3 and event 2, and we get this here. If we add the 2 durations for the outgoing trip and the return trip, we get the total duration for moving observers, and we find that the moving duration was equal to 2 divided by gamma times L over V. Now compare that to what the stationary observer, observer A, experienced, and that's just a time of 2 times L divided by V, which is the same as the moving observer, but without the gamma. So when you get down to the final nitty-gritty, you find that the duration of the moving observer is just the duration of the stationary observer divided by gamma. Okay, so we're out of the math. What does this tell us? Since gamma is a number that is always greater than or equal to 1, that says that the moving person's duration is smaller than the stationary person's duration. That's just what it means. So that gets us back to the paradox thing. If you can't know who is moving and who isn't, what I've done here doesn't seem to have solved the mystery, but it has. Forget the math and focus on one crucial difference. Observer A existed in one and only one reference frame. The moving observers existed in two. That's the only difference. So that's the answer. The twin paradox isn't a paradox. Further, the solution doesn't depend on the accelerations. After all, no accelerations occurred in the example. And the bottom line is that if a person leaves the Earth and flies to another star at high velocity and returns, the traveler will age much slower than a person who stays on.
Okay. All right. So that was his presentation. As we I have a chatter here on Twitch, who shrewdly pointed out that that actually makes more acceleration because he had A, B, and C. Remember, and B and C are both have to accelerate at least at the start, right? And then it'll be two of them. But there are versions of that scenario that Don just laid out there, and I think that's his. It sounded like he was the one who made it up. I don't know if that's what it sounded like to me. The way he was presenting that, it sounded like something that he made up. This was in 2018 when he did that, and I didn't see anybody else who had talked about that scenario before then. But anyway, there's a scenario where everybody starts, the B and C start out in motion at the very beginning of the thing. They're already moving, right? And so there is no classical acceleration. And there are a couple guys who have done. He left off some stuff, like I said, the length contraction and a few other things in there. And he, at the very beginning, he said he was going to leave some stuff out. So it's not on him, right? He said he was going to leave some details out. There are some guys out there who actually did it with all the gory details, like he said. There was Brian Greene did a thing on it, and I've got all these links are in the description of the video. When it gets up to YouTube and on Twitch, we'll have it in the descriptions there so you can see the links to all these. Brian Greene did a twin paradox thing where he talked about that scenario with the three different twins, triplets, right? And they were already moving. He went into great detail on that. And who else did that? Mahesh, FloatHeadPhysics did it, and then there was another guy too. Anyway, I got him in my credits there, so you can go and check out their videos on it too. Mahesh did it without using space-time diagrams, even more clearly than what Don just did. Don did it without space-time diagrams, just showing those things moving back and forth like that. But Mahesh did it even more clearly, including the length contraction without space-time diagrams. It was amazing the work he put into that to get that, do it, for people who don't understand graphs. So if you're one of those people who don't understand space-time diagrams or graphs, and generally check out FloatHeadPhysics. He's got a really good one on that. But they said that there's no acceleration, but I claim there is. I think there is acceleration on that. So let's take a look here. All right, this is my space-time diagram, right? Space-time diagram. And they turn around here, but instead of let's turn this one back on. There we go. So the Earth is moving, right? And the Earth, they're saying there's three Earths, right? So we got a second Earth here. Okay, now wait a second. Wait a second. Okay, so we got a second Earth. All right. Can we do that? Can you do a second Earth? Is that possible to do a second Earth? I don't think so. Let's see. I got a video here. A couple clips here. See if we can do a second Earth.
I say again, there are definitely two planets, identical but reversed in some way.
This will be a trip like no other. Travel to Earth 2.
Report that it is in the same orbit as Earth, but directly on the opposite side of the Sun.
Man you know, as Colonel Ross, is on the other planet, standing in an identical, except reversed room, talking to an identical Jason Webb who's...
Okay, that was a couple clips there from two different movies that were talking about two Earths. There was a more recently there was one called Another Earth, 2011, 2012, something like that, where it was, there was another Earth that somehow came by, and they had two Earths, right, with identical people on both Earths and the whole thing. And there was one that had done it many, many years earlier in the 1960s, 63, 64, 65, something like that, called Doppelganger, which got renamed, or they changed the name to something else, the Earth on the other side, planet on the other side of the Sun, or something like that. So I took some clips from it just for fun. So we're going to do that too. We're going to have another Earth. We're going to show multiple Earths here, and that's just fine. There's no problem, right? There's a thought experiment. We can think whatever we want. So I got a second Earth here, right? And this Earth's going to start over here somewhere. And we'll go ahead and say that this Earth is already in motion in this direction, right? Starting down here somewhere, right? And its timeline then is going to be across here. Do I have that? I don't think I have that on here anywhere. Let me see here. Hang on just a second. Technical difficulties. We'll get it figured out. No, I don't have it. All right, let me get rid of my lines of simultaneity here because we don't need that right now. So this Earth starts over here on this side, and it's heading already in motion. And its world line on this graph here, what it looks like on the space-time diagram, is it's going to start over here somewhere, 12, 10, whatever, 20. I don't know where it starts at over here, 12, I guess. And it's going to head up this way. And it's going to just keep on going along this timeline here. Meanwhile, this Earth here is going to follow this world line. And everything's timed out. It's already moving, let's say, right? So it doesn't have to accelerate at the beginning. And everything's timed out so the two Earths cross right here. They don't bump into each other, though. Even though there's only one dimension of space. We figured out which somehow they don't bump into each other. Okay. And it just keeps going right up this way. Now this is not the twin paradox, right? It's not, we're way far away from the twin paradox at this point. But they're trying to say that they're trying to show that you could have two inertial frames in a scenario where there would be no acceleration. However, there is acceleration. Because when you noticed in the video, Don said as they pass each other, as the two spaceship Earths pass each other, one of them holds up a sign that says, "This is what time it is for me," or whatever, and the other one's supposed to look at it and write it down or whatever. Okay, that you can't do that at 0.6c. You can't. There's no. if you've ever been in a plane where you passed another plane doing 400 or 500 miles per hour in opposite directions, you can't see anything. You just see and at points, let alone at 0.6 C. At 0.6 C, you're not going to see anything. You're not even going to see them go by you. So that won't work. But so Mahesh, when he did it on his video, he used a radio transmission. And he even put in the Doppler shift and everything. He's just got it wired. He did a really good job on it. But even with a radio transmission, remember I said that the relativistic idea of acceleration is a change in inertial frame over time. Now they're saying, well, there is no time because it's happening instantly at that point, but it's not instantly. It takes time for that to happen. It takes time for that radio transmission to send it on a physical level and on just a practical level. It takes time for that radio signal to go from the one Earth, spaceship Earth, to the other spaceship Earth that are crossing each other, right? This one, they're crossing each other. Actually, it's like this, right? You got these two Earths that are coming towards each other, and they cross each other. As they cross, the one that's heading away from Earth sends its time data to the one that's heading towards Earth, and that takes time. It takes time just for the radio signal itself to go from this Earth to this Earth. It might just be, several nanoseconds or something. I don't know how close you could get two Earths together and still be able to do that. I guess they'd have to be quite, a few miles away, so maybe microseconds, to transmit that radio signal. So there's time involved in the transmission of that, and during that time, you have a change in inertial frames, and you could look at it from the perspective of just the information. The information the information was heading this direction, and then the information suddenly reverses and changes its inertial frame and goes back the other way. That's an acceleration under a very broad. Very, very broad. There's a guy out there who talks about information as a physical thing, and he actually wrote a paper that said that information has mass, which I don't believe, but anyway, it's within the realm of possibility, right? But even if you just look at what's physically going on, is you've got a radio transmitter, right, in one spaceship. And it's causing electrons to go back and forth, to move back and forth. They are losing some of their energy, right? Energy and mass is the same thing, right? They're losing some of their energy. That energy is being going through space. It's landing on a charge carrier on the other one in their receiver radio, causing an electron to move on the antenna, say, of the receiving radio. And that energy is being deposited in that other spaceship that's heading the other direction. So there is something that is changing directions, right? There is energy, mass energy or equivalent. There is energy that was heading this way, and now it's heading this way. So it changed its vector. It changed its velocity. So it accelerated. So even in this scenario, there's an acceleration going on, in my opinion. But that's my opinion. Everybody's got opinions, right? All right, so that's what happens here. This Earth here travels this direction. This one travels that direction. They cross right here, and it goes back to again these lines of simultaneity, right? When it's going out, the lines of simultaneity are this way, and when it's coming back in, the lines of simultaneity are this way, and that's how they're saying this the time changes, and that's how to differentiate between the two. But that still didn't fix our problem, did it? It's still, look at this. See, it's still. Even with that scenario where you got one Earth going out and the other Earth coming in, and they cross and then come up here, the twin on the Earth is still going to be younger, or the clock on the Earth is still going to be slower than the clock on the rocket ship that has just been in this inertial frame. So that didn't fix our problem at all. So we're kind of stuck here, right? We went through all the different things here. We tried to figure this out, and we're stuck. It's a paradox, isn't it? Almost. So what do we do? When you get stuck, when you're trying to figure something out and you get stuck, the thing to do is to go back to first postulates and data, and go down to the fundamental, right? The ground floor, and figure out what is going down, what is the deal, right? So let's go all the way back to the very, very beginning, right? Very, 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 very beginning, which is going to be all the way back to Einstein, right? That's where all this started, right? It's his fault. Let's go all the way back to Einstein and look what he said about it, right? Maybe we can get some clues there on what's going on, all right? So here's sorry, this is kind of bright here. I don't know how to fix that. I could. Yeah, we're stuck with this being real bright like this. Sorry. So this is what Einstein wrote about it, contemporaneous to his paper, right? He wrote the paper in 1905 on special relativity, and then in his paper he talked about a scenario in which something moves in a circle, while another inertial frame is just at rest, which was kind of unusual. But anyway, he wrote about this idea of not quite the twin paradox, but here I'll just go ahead and read this to you, and we'll see what he says about it. So he's explaining special relativity, and then he gets down to this paragraph, a couple paragraphs here. He says, the thing is at its funniest when one imagines that the following is being done. One imparts to this clock a very great velocity, almost equal to c, and lets it fly on its uniform motion, and after the clock has covered a long stretch, one imparts to it a momentum in the opposite direction so that it returns to the point from which it had been launched. It then turns out that the positions of the clock's hands have hardly changed during the clock's entire trip, while an identical constituted clock that remained at rest at the launching point during the entire time changed the setting of its hands quite substantially. It should be added that whatever holds for this clock, which we introduced as a simple representation of all physical phenomena, holds also for a closed physical system of any other constitution. Here we, for example, to place a living organism, organism in a box and make it perform the same to and fro motion as the clock discussed above, it would be possible to have this organism return to its original starting point after an arbitrarily long flight, having undergone an arbitrarily small change, while identically constituted organisms that remain at rest at the point of origin have long since given way to new organisms. The long time spent on the trip represent only an instant for the moving organism if the motion occurred with approximately the velocity of light. This is an inevitable consequence of our fundamental principles imposed on us by experience. So that's very close to the twin paradox, right? But it's not exactly the twin paradox, right? It's not the spaceship leaving Earth. It's not, but this is very early on, right? This is when he first came up with his idea of special relativity, and he talked about organisms aging at different speeds. So that's pretty close to what we're looking for. Now he kind of got around the acceleration thing here. He said. It then turns out, let me see if I can I write it with this thing? Let's see here. Hang on a second. I'm trying to get, there we go. Is this writing? There we go. So right here he says it turns out if one imparts to this clock a very great velocity. He doesn't really say, right, that's acceleration, right? He doesn't say it, but that's imparts velocity. That's an acceleration, right? And lets it fly, and then imparts another thing back onto it, right? So he doesn't really say there's acceleration. He kind of just says that it just happens, right? And so even Einstein was making stuff up. A lot of experiments, right? He kind of went around the idea of acceleration there. Let's see who else is out there. There are other people who wrote. Now that wasn't technically the twin paradox, right? That was just Einstein talking about organisms and stuff like that. All right, here's another one that talks about the twin paradox specifically. Now this one says. This is back in 1922. So it's around just right after Einstein was talking about his stuff, right? This guy is Hermann Weyl. And he says, let us imagine two perfectly identical human beings, twins, who at the instant their clocks coincide separate. One remains on Earth, the other undertakes a journey that's at speeds approaching that of light and then returns. Upon reunion, the traveling twin will have experienced less proper time and will therefore be younger than his stay at home. So we're getting close here to what the deal is, right? He didn't talk about acceleration. He just says they just take a journey. But he says one of them remains on Earth, and he says the other one travels, and then he says the other one. So we're getting close here. We're getting close to what the deal is here, I think. Let's look at another one here. This one is a little later. This is in 1959, I think. This is 1959. And this guy is at Hughes Aircraft Company, and he's writing about it. He's talking about twins here. He says the clock or the twin effect of the theory of relativity is essentially this. Consider a pair of twins. Immediately after birth, they are separated. Okay. So now he's talking about twins and separating the twins. And he says, immediately after their birth, they are separated. One of them, the first one, remains on Earth. The second one is put into a rocket ship and flown to Alpha Centauri. Now, he is specifying where the rocket's going. He's going to Alpha Centauri, okay? At a pretty high speed, 99% of the speed of light. Okay, that's close to what we were at, okay? And it says Alpha Centauri is the nearest star. It is about 4 light years away from us. As soon as the second twin gets to Alpha Centauri, he turns around and flies back to Earth at the same high speed. Immediately. Right? No, he says as soon as he gets there, he turns around. So he's got instant acceleration too. So his twin's going to be squished also. Oh well. When the two twins meet again, the first one, the one who stayed behind on Earth, will be 8 years old. Because they only went to Alpha Centauri. They didn't go 10 years. 10 years. It was closer than that. He will be 8 years old in every sense of the word. For example, he will be able to talk quite well and read a little bit. He may have just finished second grade and be about to enter into third. The second twin, the one who took the journey on his return, will be approximately 1 year old. Again, he will be 1 year old in every sense of the word. He will still need diapers. He will be barely able to walk, and he won't be able to talk much. This effect is also known as the clock or the twin paradox. Okay, it is the paradox that we wish to discuss today. Okay, and he goes on and talks about it. But that, okay, now this answered a question that we had at the very, very beginning of my talk here. We had a question about the twin paradox, in which at the very end, remember we had this. You see that? Oh, wait. Let me try harder. There we go. Remember at the very end we had the baby? And I said, where'd the baby come from? Why is there a baby there instead of the twin? Right? This guy in this other on this this paper here explained it. Right? This guy over here explained why. Remember this one? This guy explained it. He said in his thing, let me get it. Where is it? Right here. Immediately after birth, they are separated. Right? So that explains it. That explains why there's a baby in that video there, instead of a a grown adult. It's because when they started out, they were both babies. You get it? You see what's going on there? When they started out, both of these twins were babies. They were separated at birth, and one of them went on the spaceship, and one of them stayed on Earth. And the one that went on the spaceship, when it got back, had only aged, 10 months, 11 months, whatever. It's the gamma factor is like 23 or 24 or something like that. It's a huge gamma factor. And so this twin here is in her early 20s, and this one is just 10, 11 months old or whatever. So that explains that. So at least we solved one mystery there, right? We solved one mystery. Good, by going back to the the original postulates, the original facts, the first data that we can find on the thing. The empirical evidence is what we're looking for here. Empirical evidence.
I'm talking empirical evidence.
Yeah, empirical evidence. Right. We went back to the instead of looking at YouTube videos, we went to the source documents there. So that's always a good thing. Right? It's always a good thing to work from firm foundations, and get the right deal there. So yeah, always trust the data.
And you gotta trust the data.
Yeah, always trust the data. All right, so we got something solved there, but there was another clue in there. There was another clue in this thing. In one of them here, the original one here. Let me see if I can bring that back up here. Oh, here it is. This one here. No, I don't want to see anything. All right, this is commentary by Robert Resnick back in what was it, 60s? 68. So this is a few years after that one that we just looked at. Okay, that one was 59. This is 68, and this guy explains it. Okay, I think our solution here is in this this one. Whoops, I got to turn this on here. There we go. So this is Robert Resnick, and here's a couple quotes from his book or whatever he wrote a book on it or something. And it says, if the stationary organism is a man and the traveling one is his twin, then the traveler returns home to find his twin brother much aged compared to him. The paradox centers on the contention that in relativity, either twin could regard the other as the traveler, in which case each should find the other younger, a logical contradiction. This contention assumes that the twin situations are symmetrical and interchangeable, an assumption that is not correct. Ah, see. Now we didn't assume, we assumed that the Earth moved, right? Because we looked at that video and the Earth went away. All right. It says, furthermore, the accessible experiments have been done and support Einstein's prediction. Okay, so that was the passage from his book. And then in the next paragraph in the book, it says, the apparent contradiction vanishes as soon as one recognizes that the traveling twin's frame is not the same throughout the journey. In order to turn around, he must fire his rockets and thus leave one inertial frame for another. Now we said that the Earth did that, right? We said that the Earth went away, and we didn't talk about how it turned around. maybe there's, if it's got inertial dampeners for the whole Earth, maybe it's got some propulsion system that we don't know about too. I don't know. So, but that's what we said. All right. Now he says the contradiction vanishes as soon as we recognize that the traveling twin's frame is not the same throughout the journey. In order to turn around, he must fire his rockets and thus leave one inertial frame for another. The standard time dilation formula, delta t prime equal gamma delta t, applies only between clocks at rest in a single inertial frame. So it cannot be used symmetrically for a world line that involves acceleration. Hence, the twin situations are not interchangeable and no real paradox exists. Now, all of these things, all of these explanations about the twin paradox, they all got something critical here. They say stationary organism traveling twin turns around. Okay, this one doesn't really say. See, it's still not saying which one is traveling, right? But this one before, in 1922, here's where here's the deal right here, right? We skipped right over it. This is 1922, right? This is going all the way back almost to the beginning. This is the first mention that I can find of the twin paradox. You'll find other ones out there on the internet that are earlier than this, but I could not find valid contemporaneous evidence for those. This one has real evidence behind it. Let us imagine two perfectly identical human beings, twins, who at the instant their clocks coincide separate. One remains on Earth. The other undertakes a journey. So there's the answer right there. The one of them remains on Earth. The other one takes the journey. So it's the one in the spaceship. It's the one in the spaceship that's the one that's taking the journey, because it says so in the thing. Because it says so right here. That's why the one in the rocket is the one that's taking the journey, because it says so in the frickin' thing here. Right? One takes a journey approaching the speed of light. That's it. Has all these explanations that talk about acceleration and this and moving into triplets instead of twins. The answer is in the actual thing itself, in the setup itself. It says one of them remains on Earth, the other one travels. That's the one that's in motion. The one on Earth is in the inertial frame. So that's why there's a different, Now you can't, rightfully so, they're saying, well, the one that feels the acceleration. But there are scenarios where you could have, let's say you have two spaceships, right? And they both take off, right? At speeds like this, right? At the same speed, so they're both accelerating away from each other. And then at some point, this one turns around first and comes back to the origin, while this one keeps going. And then this one turns around and comes back to the origin. So which one is older and which one is younger? Well, it turns out the one that took the longer trip is going to be the younger. But they have both undergone acceleration. So from their own standpoints, they're the ones that are moving, right? So you can't just go by acceleration alone. There's more to it than that, you know. And it really is arbitrary. You know, I mean, you can figure out technically if you decide which one is going to be the one that turns around sooner, or which one is the one that actually moves. And the answer is right here. It's the twin on Earth that's the one that is at the rest frame, and the one that undertakes the journey is the one that's moving. That's it. It's just because they say so. It's because they say so in the twin paradox. That resolves the paradox right there. All that other stuff is fun to learn about special relativity, going through it, but it's not. You know, and even like when Don Lincoln did his thing, right? When he did his triplets, right? where you got one going out and the other one coming back in. You know, he decided that the one going out was going to be the rocket ship, and there would be a second rocket ship coming back in, right? That was assumed, and all these guys, everybody who has done that and covered that particular scenario where you've got three different players, they all assume that the one that you got two rocket ships instead of two Earths, right? It's just whichever one you assume to be the one that's moving is going to be the one that moves. And in the original document, in the original thing, they say that it's the twin. It's the twin that on Earth is the one that's in the rest frame. They actually say it in the thing. So so there you go. There's a solution to the twin because it's because they say so. That's the solution. All right, there's some more stuff here. How much? You got an hour and a half. I can do this. I want to keep it under 2 hours. Otherwise, nobody will ever click on this video on YouTube. It's way too long. It's already too long, I think. There is a let's talk about general relativity. General relativity is where you've got curvature of space-time. Now you don't need to invoke general relativity to explain the twin paradox. You can do it all with special relativity, and you can talk about acceleration. Special relativity. One of the postulates is that everybody's in an inertial frame, but you can say that their inertial frame changes with acceleration. It's technically not special relativity, but you can map it pretty easily on a space-time diagram. It's not that big of a deal, and we talked about that quite a bit, right? So that's not that big deal. However, when you're talking about general relativity, that's curved space-time. You've probably seen things that look like this. Did that show up? Right, where you've got some planet here, massive, like a black hole or a neutron star or a planet or anything, and they call it a gravity well. Now this is not how it is, right? This is not what curvature of space-time looks like. Space-time is 4 dimensions. This image here is actually 2 dimensions, right? It's on your screen. It's on the screen of your device in 2 dimensions. And that 2-dimensional thing is kind of using optical illusions to trick you into thinking that it's 3 dimensions. But it's still not, and it shows one of them going down, which is not right. So this is not right. Okay, this is not what curvature of space-time looks like. This is more like a space-time diagram, right? It's just showing you a kind of a metaphor or a representation of what, because we can't, right? We're just mere, we're humans. We don't know, we can't see 4 dimensions. So they got to represent it somehow, and that's how they do it. And they call it a gravity well because the way they represent it, it shows it going down. But anyway, there are a lot of problems with this thing. But the idea is that you've got a curvature here, and this curvature can represent how much gravity is going on, right? Way down here, deep in the gravity well, there's a lot more gravity, or there's more curvature of space-time, which shows up or manifests itself looking like a force of gravity that's greater down here in the gravity well than it is out here, at the fringe of the gravity well. So an observer out here is going to experience less gravity. Someone in here is going to have more gravity. And as it turns out, when you look at the space-time diagram, one more thing. When you're deeper in the gravity well like that, time goes slower for you compared to somebody who's outside or further away in a lower gravity. So any object that's in higher gravity, like that deep in a well like that, their clock is going to tick slower. Time is going to be slower for them compared to someone out here. So someone out here observing someone deep inside a gravity well is going to see this one deep inside the gravity well, going to see their clock ticking slower. And the converse is true. Somebody who's deep in the gravity well, looking at somebody out here in a lower gravity, this one in the gravity well is going to see this person out here, going to see their clock speeding up, running really, really fast. And that's how general relativity works. So I wanted to show you here on this, on the space-time diagram, something that's really kind of cool. At this turnaround here, when we already talked about what happens here at this turnaround point, the lines of simultaneity shift. So if you look at the lines of simultaneity for this one, where is it? Prime time simultaneity. There we go. Before the turnaround, the lines of simultaneity, the lines of same time, right? This line of same time is going to be down here somewhere in the reference frame of the rocket, right? This is the rocket's reference frame, and Earth when it went away and came back. I guess we can switch this around now, right? Because we know this is the Earth's now instead of you understand what I'm talking about, right? So this is the Earth's reference frame instead of the rocket. Let me shut that off. That's just confusing people. So the rocket goes away, and before it turns around, it thinks it thinks that it's the rest frame, and it sees the person on Earth, the twin on Earth, at 4 or whatever years, instead of its 8 years that it has gone here. But then after the turnaround, then its lines of simultaneity change and move up here because it's moving this direction. And so at that same point, just as it makes the turn, it's going to see the Earth clock at, almost 13 point something, 8 or whatever years. So it's skipping. It's seeing this from the perspective of the spaceship here that is turning around and experiencing G-forces here, acceleration. It's not only is it experiencing G-forces, but it's witnessing or seeing a shift in its lines of simultaneity from down here up to here relative to where the Earth is. So what it's seeing is that only a few minutes or a short amount of time is going on for it. But when it looks at what's going on here at Earth, it's seeing Earth's time go really fast. Now that's the same thing that happens with if you had a huge, like a black hole or a neutron star or something like that next to it. Next to the spaceship. Let me see if I can draw that here. Let me try this here. I don't know if I can do this or not. Yeah, I think this will work. So imagine you had a big... Okay, I'm not doing this too well. I'm doing this with my mouse. So, all right, give me a break here. All right, so there you go. Imagine this is a huge black hole or neutron star or something big that has a lot of gravity to it. Then this spaceship would be closer to this huge black hole than the Earth would be out here, the other twin. So this twin being closer to the black hole, this twin's clocks are going to tick much more slowly than this twin out here. So general relativity it's very similar to what's going on here is what I'm saying. Einstein talked about the equivalence principle, where he said someone in a spaceship or whatever that experiences acceleration, they can't tell the difference between that acceleration at a local point from the gravitation that you would feel as if you're on the surface of a planet or near a black hole or whatever. Right? That's the equivalence principle. That acceleration is equivalent to gravity at a point. But that's a very key point. At a point, at a specific location, because when you look at the gravity from this huge neutron star or whatever, it falls off, right? It falls off with the square root of distance. That's why this gravity is less over here than it is here. So this only works if you set up a specific mass and specific distances for these. You couldn't, for example, change the situation so that this twin only goes out, 5 years and turns around with this mass here, because this is not a linear function here. The fall off of gravity is not a linear function, right? It's curved. Let me show that curved gravity well here again. Right? It's curved. It's a curved space, whereas that space-time on the space-time diagram, when the lines of simultaneity change, it's a linear thing. These lines, it's linear. See, these are all lines, and it turns out to be a triangle here. Let's see, lines of simultaneity. This is extra credit stuff here, guys, so don't, if it's not, doesn't make sense to you, that's okay. This is all extra credit. It has nothing to do with we're all done with the twin paradox. This is more extra goodies here. So there's an angle here. It's a triangle, right? At this point here, the lines of simultaneity make a triangle. And there are two things that determine how much time are going to be skipped here. One of those is how fast this traveling twin is traveling. The faster it's traveling, the more angle will be between these two lines of simultaneity. So if it's traveling at 99.9% of the speed of light, or near, basically at the speed of light, the angle here between these two lines of simultaneity would be 90 degrees. If it's only traveling at 0.1% of the speed of light, then this the angle between these two lines of simultaneity will be very close. So that's one thing that determines how much is skipped here. The other is how long it travels before it turns around. If it traveled just a short distance, even though it was traveling at the same speed here, and came back, then it would be less distance because the height of this triangle right here, is going to be shorter. Let me see if I can draw that triangle for you here so you can see it. I'm doing this freehand, which is not how I should be doing this, but that's okay. See this triangle here? That triangle is the lines of simultaneity. So the faster this twin is going, the wider this angle will be. The wider this angle is, the more time gets ticked off during the turnaround. The more time that the stationary twin gets skipped by while this twin over here is turning around. And also, the further away that this twin travels, the taller this triangle is going to be, which means that these are going to be wider too. So, but all those are all linear functions, right? It's all linear. Whereas with the gravity well, it's a square of the distance. It's not linear. It's exponential, or at least geometric. Let's see. I had a little diagram here of that, and let me see if I can find that here. Sorry, I lost track here of where my thing. I did an actual diagram here of what that looks like, and I wanted to show that to you. Here it is. Okay. Let me open that in this. There we go. No, that's not it. There we go. Do you see that? Maybe not. All right, I just take it. Hang on just a second here. I'll get this figured out. I told you this is live. Right, you're gonna have stuff happening here. Space-time diagram. I got to shut that off. That's not it. Okay, hang on just a second. We'll get this figured out. Here we go. Okay, I got it now. There we go. Okay, so this shows this red line here is showing the gravity well, right? It's showing how much gravity there is. Here's the center of the planet. And this is how far away you are, the radius from the center of the planet. And this red line shows you how much gravity there is, except it's inverse to make it look more like a well. So the further down you go, the more gravity there is, okay? So that's what it looks like if you're at 2 points. If you were at these two different points here, if you were at this point here, you would have less gravity than say a twin down at this point in the gravity well, right? And that could work out as a linear function too, with those two. Say the speed of the twin, or the distance that they traveled, would be a linear function, and you could end up crossing at those 2 points. But it would only work for those 2 points, right? If this twin moved out to here somewhere, was this far out instead, then they don't intersect. So it's the bottom line is you can compare general relativity and kind of squeeze it into this twin paradox, but it's not the real thing. It's not what's really going on there. That shift of lines of simultaneity during the change in inertial frames is a linear thing. It's not a square the distance like with a gravity will. And that's why the equivalence principle only works at a point. And I did a stream on this. I did a stream on the equivalence principle. You can go back and look at it, and I explained it. I think I did a pretty good job of explaining it, better than I did just now. Anyway, so you can go back there and look at it, and where I explain why the equivalence principle doesn't work, because whoever's in the spaceship that's under acceleration is going to know that it's accelerating, because the gravity, or the faux gravity, is going to be the same at the floor as it is at the ceiling. Whereas if the spaceship was just sitting on Earth and he was feeling the acceleration of gravity, the gravity would be higher at the bottom of the ship than it would have at the top. That's the difference. So it's you just can't use general relativity to explain that, I guess is what I'm saying. There have been, that doesn't stop people though. A lot of people out there doing papers on general relativity. There was a guy out there who did a couple guys out there who did general relativity, the twin paradox and general relativity. And what they did is they took, let's see if I've got an image of that. Yeah, here we go. All right, I got to change this here again. Sorry. Did you see that? No. All right, this will just take a second here. All right, sorry. Technical problems. It's going to take a second to get this figured out here. All right, open. I'm clicking around here on my computer. Sorry, I'm trying this, because this is kind of cool though. So I want to show it to folks. It's just going to take me a few clicks to get it up on the screen here. My computer is getting tired and it's slowing down. I'm getting tired and I'm slowing down. Let's see here. There we go. Ta-da! All right. Did that work? No. There we go. Okay, so these guys wrote this paper. The name of the paper is Adding to the Confusion. The accelerated twin is younger, I think is what they're, or is older rather. It's just they decided to do the twin paradox in a circular thing instead. They got one twin here, which is constantly, around a planet or whatever, gravity well, okay. And you got one twin that's just in a rocket that is holding steady right here, but they have to accelerate in order to hold steady because there's gravity, right? So to stay in one place, they have to accelerate. The other one somehow gets, without accelerating, gets bumped so that it goes in an orbit around the Earth and comes back to the same spot. And this one that travels without accelerating, just free fall orbiting, is younger because of special relativity, because it's the one in motion compared to this one. If you pick this one as the one that's standing still. But the problem with this is that, you don't have to have a rocket firing here, accelerating that way. You can do it. Let's see here. I guess I didn't save it. Here, I'll just draw it in right now. You can have this rocket instead actually sitting on a mountain or something. Let me just draw this in here real quick so you can see. I can illustrate what this is. What's going on here. Instead of having this rocket here firing its rocket in order to stay in place, you could have say a big mountain here or something, right? That it's sitting on the Earth. Instead, same deal, right? So it's not firing its rocket to accelerate. It's just sitting on Earth, accelerating. It is accelerating because it's on the surface of the Earth. Everybody on the surface of the Earth is accelerating, believe it or not. That's the way it works. But then what you got is you got one twin sitting on Earth, right, which is the original twin paradox, and the other twin going up and flying around and moving and coming back, right? And it's a lot of people complained about that paper. Those guys who wrote that paper, they didn't like it, and they criticized it and did, and it's just, they're forcing general relativity into the twin paradox when it doesn't need to be there. It's that's just it's one of the problems, right? It's one of the issues. Let me show you something else here because this is kind of interesting. All right, this should just take a second here. Yeah, my computer is really slowing down here. Sorry about that. Here we go. Okay, I'm waiting for my computer. There we go. All right. Here we go. So that experiment that I just talked about with one twin on the Earth and the other one going in orbit around the Earth and then coming back, that's been done already. That's already been done. Here, see this? Remember that? Scott Kelly went up into space, right? And orbited space while Mark Kelly stayed on Earth. That experiment has already been done. They figured it out, As it turned out, it was actually it's kind of complicated, but there's the higher up in orbit you go, the more the more general relativity effects come into play than low in orbit. Here, let me show you a graph. You like graphs, right? Let me show you another graph. Orbital time dilation. Here we go. So here's a graph that shows what's going on between special relativity and general relativity in orbits. Oh, you can't see that. I guess I got to zoom out. Let me show you what's going on here. Here's a planet right here that I've got on the table here. This planet. When like the GPS satellites and all them, they orbit way out here somewhere. They're pretty high up, pretty high orbits. Middle orbits, I guess, right around here. But the space station and Starlink and a lot of these low Earth orbit spacecraft, they're just like a couple millimeters off the surface of the Earth. They're basically at the same point in the gravity well as somebody sitting on Earth. There's not much difference, I mean, they literally travel just like that much off the surface. It's really, really close, just above the atmosphere. And they actually, like the Starlink satellites are actually slowing down because of the atmosphere, because they're kind of clipping the top of the molecules, just outside of the atmosphere. Anyway, the spacecraft that are close to Earth. So let's see here. This represents how high the orbit is. Okay, so this line right here is hang on just a second. This is Earth's surface here. This line. So this is something on Earth is going to experience this much. It will experience no speed up from gravity because it's at the surface of Earth. But as a spaceship gets further and further away from the Earth in its orbit, higher and higher and higher, it's going to experience more speed up. So this is higher and higher and higher orbit. So when it gets up to 30,000 kilometers above the Earth's center, then it's going to be at a lower gravity. It will be in lower gravity, a higher point than the gravity will. So it will experience less gravity, and so its clocks will speed up or will slow down compared to somebody on Earth. But because they're flying through the air, they're moving. Special relativity has an effect. So at low Earth orbit, the effect is quite a bit due to special relativity, because a lower orbit requires that the spacecraft fly at a much higher speed, right? Because there's more gravity, right? It's got to fly at a higher speed to stay in orbit. Whereas way high up there, 30,000 kilometers from the center of the Earth, the orbital speed is much slower. And you add those two together, and it turns out that somebody at who is less than 10,000 kilometers from the Earth's center will have a net, their clocks will run at a net slower speed. But once they get higher up in orbit, once they get above 10,000 kilometers or so, their spaceship is moving slower at a slower speed, and they're at a much lower gravity, higher in the gravity wheel, so they have less gravity, and therefore their clocks will be running faster compared to somebody on Earth. I hope I explained that. Anyway, that's some general relativity stuff that you can make it fit into the twin paradox if you want. People have tried to do that. And as I said, Einstein's original paper on the thing, that was the example he gave. The original, paper he did on the electrodynamics of moving bodies. That was the 1905 paper that just shattered everything. In that paper, in the paper itself, he gave an example of a body going in a circle compared to one in the center. And I think what he was trying to get at there, this was before he did general relativity, and I think he was trying to get to try to set things up for an experiment. He didn't know about general relativity yet. All he knew about was special relativity. But I think he was trying to set up an experiment where you could have a high precision clock on the equator and another high precision clock at the pole. And as the Earth turns, this one at the equator is going to move more relative to this one up here at the pole. And so this one should have less, the clock should tick slower on this one. But because of general relativity and because of the gravity and all that stuff and a whole bunch of other effects that he probably wasn't thinking about at the time, that experiment I don't think would work. Right. It wouldn't give the results that they would expect. And it turns out that he went ahead and did general relativity and never, as far as I know, he never pursued that any further than just mentioned it in his paper when it came out. All right, I guess that's it. So we did 2 hours on a twin paradox, believe it or not. If you have any questions, go ahead and give them. Oh, let's see. I've got. Let's see. I got to check chat here to see if I've got chatters. Oh, I do have a chatter here. First time chatter. Hi. How are you? So, all right. If you have any questions, go ahead and put them in YouTube. I've got the links for all these various videos and stuff that I've played here. I've got them all in the description, I think. I hope. If I missed one, sorry. Let me know, and I'll add that to the description too on YouTube. If you have any questions, go ahead and put them in YouTube. And get what I'm supposed to say. Give me a follow, give me a subscribe, all that. Comment on my video, all this stuff, right? That's what everybody wants. On Twitch, I'm at Double Tribble. Is my Twitch channel. And on YouTube, it's doubletribble-yt. And I have a website, doubletribble.com. So if you watch, I don't have all my videos up on the website, but the ones that I do, you can watch them without any ads or anything. So that's kind of cool. But yeah, give me a subscribe on YouTube. Give me a follow or whatever on Twitch. And that'll help out. All right, let me see if there's any. Oh, Snowy City. Interesting. I've heard time goes at a different rate at sea level versus the mountains. Yeah, it does, because it's a teeny bit. I don't know if they can even measure it. I think they can with atomic clocks. They can measure that difference. But yeah, it's a little bit, when you're at the top of a mountain, it's less gravity. Just a tiny little bit less gravity at the top of a mountain than it is at sea level. So that's why that happens. But of course you could never, you could never notice that, right? It has to be measured only with really accurate atomic clocks and all that. Let's see. Okay, I guess that's it. All right. Well, everybody, thank you for coming. Oh, let me put I'm going to put my the links to my my socials and all that stuff in here. So you can follow me in Twitter, subscribe or follow or click or like or whatever. I don't know, whatever you want to do. All right, I'm going to play the credits now. And let's see, I don't have enough people to rate anybody. So, all right, I guess that's it, everybody. Thank you very much. Thank you for watching. If you have any questions, remember, type them into the comments. Bye.